A cannon fires a cannonball at an angle of 55 degrees to the horizontal with a speed of 12 meters per second. This is an example of a projectile at an angle, and the flight path is a parabola. Again, there is only one acceleration acting on the projectile, and that is acceleration due to the force of gravity. It is constant throughout the flight, acting downwards. When we look at the horizontal and vertical components of the projectile velocity, it is observed that the horizontal component of the velocity is constant throughout the flight, but the vertical component of the velocity changes throughout the flight due to the downward acceleration from the force of gravity. The vertical component of the velocity is reduced to zero as the projectile rises upwards. At the top of the flight, the vertical velocity is reduced to zero. On the way down, the force of gravity accelerates the projectile, increasing its velocity in a downward direction. Here is a snapshot of the vertical components of the velocity at half-second intervals. To construct a velocity time graph, we arrange the vectors along the time axis, like this, starting with the vertical component at 0 seconds. Let me place it there. And we can see it's just approximately 10 meters per second upwards. We take the next one at 0.5 seconds and place it there. And we know that at the top of the flight we're going to have zero vertical velocity, so that point there is going to be zero. Then 1.5 seconds later we move to here, and our final vector is at 2 seconds, is here. Now we take our ruler, we can see that the tops of each of the components of the vectors all lie in a straight line. So we can draw a line to represent our velocity time graph. So the graph is a straight line, which confirms that there is a constant negative downward acceleration acting on the cannonball. Let's work out the gradient of the velocity time graph. That will give us a value of the acceleration. So the acceleration is going to be equal to the change in velocity divided by the change in time. That's from our definition of working out the acceleration from a velocity time graph. So which 2 points we choose? Well, 2 as far away as possible. We'll choose this one up here and this one down here. And now we'll construct our lines. So that will be our change in velocity, and along here will be our change in time. And you can see from the graph that the change in velocity is going to be 20 down the way, 10, another 10, and it's down the way, so it'll be 20. So the change in velocity is minus 20. What about the change in time? The change in time goes from 0 up to 2 seconds. So we only have 2 seconds for a change in time. So we have a change in velocity of 20 meters per second downwards and a change in time of 2 seconds, and therefore the acceleration comes out to be minus 10 meters per second every second, which is very close to the value of the acceleration of gravity. So we've shown from this graph that the projectile's vertical component of velocity is under the influence of the acceleration of gravity, minus 10 meters per second approximately. And we can see from the first part of the graph that the velocity components are upwards and they're decreasing until they get to 1 second and the vertical component of velocity becomes 0. Thereafterwards, the vertical component of velocity increases in the negative direction, shown on the graph as the component vectors pointing down the way. That is the famous graph of the vertical components of a projectile at an angle. So here are two graphs showing how the vertical component and the horizontal component of a projectile fired at an angle varies over the time of its flight. As you can see, the horizontal velocity doesn't change during the course of the flight. Remember, there is no air resistance. But the vertical component of the projectile's velocity does change. It's accelerating downwards with acceleration due to the force of gravity. The vertical component of the projectile starts with a value, and over time it gradually reduces to 0 at the top of its flight. So at the top of its flight, the projectile will have no vertical velocity, but it will have a horizontal velocity. And after the top of its flight, it begins to accelerate down towards the Earth again, still having a horizontal velocity, but its vertical component of velocity increasing in the opposite direction. And that's why we get the shape of the graph as shown.